All right. So today we are happy to have a Marius Kongsore as today's line seminar speaker. So he's a PhD student in NYU, New York University, and has been working on the intersection of particle theory, high energy formal theory, and astrophysics. So today he will talk about Dyon loops, axion, and symmetry in between. Please start.
Perfect. Yeah. And as I've had the pleasure of knowing you and talking to you guys, this work is very relevant to some of the things you are thinking about here, at least a subset of you. So the talk today is mostly based on this paper here I put out earlier this year with Isabel Garcia at University of Washington, and then with my PhD advisor, Ken, at NYU. I'll also just have a couple of remarks from a paper put out later last year with Nathaniel Cray. But this first paper is really the star of the story, and it'll be all about connections between Dyon loops and instantons. Good. So the outline of the talk is as follows. So part one will be motivation. So I'm going to show you that in thinking about axions and axion theory, in particular from the point of view of both non-invertible symmetries and in terms of axion mass generation, that you're sort of naturally led to think about questions involving Dyon loops and instantons. So dyons are like these particles of both magnetic and electric charge. And you'll see that these questions are phenomenologically motivated. They might have something interesting to say about phenomenology. Then part two of the talk is really where my main claim is going to lie. So this will be mostly just review of sort of the axion theory landscape that points you to this connection. Part two of the talk will be where the main claim lies, which is loops of dyons are effectively a type of Abelian instanton in a gauge theory. And then part three will be after we've studied the connections between these Dyon loops and then axions. I'm going to show you that these U1 Dyon loops, which if you know anything about monopoles, you probably know that they're singular objects in a pure U1 theory. That's the standard Dirac monopole story. So they need some kind of UV completion to have their cores described, and that's going to be part two of the talk. So that was a very quick overview of what this talk is going to be all about. So let's dive right into it. Right. So part one will just be thinking about axion and seeing how they point us to these Dyon loops. So I assume, so this is a pretty wide audience, I learned, so you might not all be familiar with the axion, so I'll just give you a brief summary of the important points. So the QCD axion, right, in this talk, you'll denote it with theta of x is just it's a pseudoscalar degree of freedom. We typically believe it to be light. And it's one of the most studied today candidates for physics beyond the standard model, because it can simultaneously explain what's called the strong CP problem, which is just saying, why is the neutron electric dipole moment so tiny in nature? And it can be the dark matter of our universe. That's why people are very interested in the axion. It kind of solves two problems at once. The other reason we really like the axion is it provides a really nice experimental target, right? So many of you have probably seen plots like these, where on the x-axis, you have the axion mass. On the y-axis, you have the axion coupling to photons. And we know that at least in the most minimal models of axions, if they're a real particle that exists in nature, they will live somewhere on this yellow line in parameter space. And what all these different colored panels show is all the various ways that people have thought about either experimental detections or astrophysical constraints or cosmological constraints on what the axion mass and coupling to photons could possibly be, right? So all this is ruled out. And we have this really nice target that we're sort of aiming to reach within the next decade or two, which is we're going to try to probe all the way down to this yellow line and find out if the axion exists or not. Of course, that's why people in my field of phenomenology are very excited about axions. I have another reason that is shared with many in this room, I believe, to be interested in axions, which is for such a simple particle, the axion is just so extremely rich field theoretically, right? It's a spinless particle, and yet the ways it interfaces with topological quantum field theory and other interesting aspects of high energy physics is just so rich. And all this really, I believe, in the end comes from the fact that the axion is compact. So the axion, right, is an angle, can take values between 0 and 2 pi, so we can represent its field space at any point in space-time by a circle. And just this fact that it wraps around itself lets it talk to topological field theory and so much other interesting high-energy physics. So here's just a very quick overview of some of the things that excite me. This is far from an incomplete list, but the axion can have interesting connections to quantum gravity, where you might know that the axion, if it's some extra-dimensional gauge field that wraps my extra dimensions that I have in a string theory, for example, then that very naturally leads to an axion at low energies that could be the dark matter of our universe. Axions also have interesting connections to the swampland via what's called the axion zero form, the axion weak gravity conjecture, or the zero form weak gravity conjecture. If you measure the axion couplings to various gauge fields, I can tell you something about this discrete subgroup that you can mod out of the standard model gauge group that we don't actually know what is. Of course, axions interface very nicely with topological defects. That'll be a central player in today's talk. So just to advertise some of my own work, I thought a lot about axion domain walls in the early universe, these literal domain walls that you have at early times that perhaps would collapse down to black holes. That's what I find in this paper. The axion also has really interesting connections to monopoles. So this happens here, what's called the Witten effect, right? So if you plonk down a monopole, you turn on an axion background, that monopole can now also get a little bit of effective electric charge. This story is kind of important to today's talk, actually. We know that the axion in, for example, QCD gets its potential from instantons. And most recently, and this will be part of the motivation for today's talk, the axion has these interesting connections to the generalized symmetries program that's been gaining a lot of wind in the last few years. So I had this paper out last year where I showed that with Nathaniel Craig that if you have these stringy extra-dimensional axions, you can think of them as being somehow protected by higher form symmetries. That's not too important to today's talk. What's really important to today's talk is this aspect. They have some interesting connections to non-invertible symmetries that people here, especially Clay Cordova, has fought quite hard about. Okay, so the takeaway is just that axions provide a really natural contact point between theory developments in QFT, quantum gravity, and particle phenomenology. And that's an intersection I certainly really appreciate. I really like it when we get the chance to talk to each other within these subfields. Good. Today, though, we're going to zoom in and leave behind these broad, bold set of ideas. And we're just going to think about the axion shift symmetry. So the axion lives on a circle, right? And you can show that a free theory of an axion has a shift symmetry with a Noether current that's the following. F here is just the axion decay constant. So it's just some dimensionful constant. If the axion has this shift symmetry, so that means I can shift theta by theta plus any constant, and I end up with the same theory I started with, then the axion will not have a potential, right? So if I'm allowed to shift theta anywhere along this axis and the theory is invariant, right, that's telling me there can't be any sort of potential humps. There can't be any axion potential because otherwise I'd be climbing up or down those potential hills. Conversely, when the axion has a potential, there's a way of thinking about this from the point of view of breaking this shift symmetry. So when this Noether current has some source, I will see that for example, if I couple the axion to gluons, it'll break this symmetry. That can give me some cosine potential. I can imagine coupling the axion to some other gauge group, call it G prime. That could give me some completely different potential on top of this blue one that has perhaps a separate minimum. Or I can have more exotic things, like if my axion comes from extra dimensions, I can wrap particles around those extra dimensions, and they can give me some periodic potential too. So this is a very well-known and very old story. Where it gets interesting is when you start thinking about the generalized symmetries of this setup. So Chicago is kind of one of the powerhouses of generalized symmetries, but in case you're not too familiar with how that story goes, here's just a one-slide primer on these generalized symmetries and symmetry defect operators. So in modern language, right, we know we can think about the axion shift symmetry not just as some Noether current with an associated Noether charge. I can in fact take the shift symmetry, so that's the current I showed you before, and I can imagine integrating it on some, in this case, 3-dimensional manifold, where I'm imagining I'm living in 4-dimensional space. I'm very much interested in our world. Then this operator here that I've defined by just integrating the axion shift symmetry current over some 3 surface, I can think of it as implementing the axion shift symmetry via topological linking, right? So I can trap an axion field insertion inside this operator. I can pull the operator through, or equivalently, I can imagine pulling the axion point out, and I shift the axion by some constant alpha. This quality should, of course, be thought of as holding sort of inside the path integral, being it's an equation and an equality between correlators. So this is a somewhat trivial story, right? This is just a different way of rephrasing the axion shift symmetry in this newer language. What's really interesting is what happens when you couple the axion to photons. So here I've taken a very simple theory. It's just an axion kinetic term, a free Maxwell theory term, and then axion photon coupling, where k here is just some integer. If we had coupled the axion to gluons, this is what you might know as the domain wall number, but for a U1 theory, that thing is slightly different. In the sort of classical symmetries language, right, we think of this coupling as breaking the U1 down to its decay. And indeed, if I just look naively at my axion current equation, now on the right-hand side, right, this current is now sourced by FF dual. That's coming from this term up here. And so, based on what I just told you, right, this should generate a potential for the axion. I just broke the shift symmetry. However, this is where sort of common lore comes in. There's no object that's really charged under this in a flat space-time. Remember, I'm a very phenomenological observer. I care about flat 3 dimensions of space and 1 dimension of time, although I'll mostly be in Euclidean formalism in this talk. And in flat space-time in R4, so Euclidean flat space-time, there are no U1 instantons. And so there's no object that's really charged under this thing. And so the right-hand side is never really realized. You don't really get an axion potential. And so this is where the modern developments come in. So where Clay Cordova and Shoping Cho and collaborators have shown that the axion shift symmetry isn't just broken and that's the end of the story. There's in fact some non-invertible symmetry that survives. And the way you think about that non-invertible symmetry is just you take this symmetry defect operator I had before, and I'm being very schematic here since this is all just still motivation. I can add some topological quantum field theory that lives on this symmetry defect operator on this 3 manifold that I showed you before. It's literally the same one. This is like completely auxiliary. There's no new physical states. It's just auxiliary degrees of freedom. But if you do that, then there is some well-defined way of thinking about this operator as still implementing a symmetry in that it has these topological linking properties. The non-invertibility, right, that shows up in how this operator acts on tuph lines. So tuph lines, if you're not used to thinking about them, you can just think of them as world lines of infinitely heavy magnetic monopoles. So this is where that sort of monopole story begins to emerge a little bit. If I take this symmetry defect operator I had before, and I pull the tuph loop through the surface, the price I pay is I get some other topological surface attachment. And so this is sort of a hallmark of a non-invertible symmetry in that when I act on it with certain operators in my theory, then I get these topological surface attachments. And I should say this tuph line is perfectly well defined as an operator, even in just a pure U1 theory. You don't need dynamical magnetic monopoles. That'll be the next part of the story. Of course, the upshot of all this is, even though we found that the symmetry becomes non-invertible, it still just implements the standard axion shift symmetry. It has this weird behavior when acting on tuph lines, but on axion field insertions, it still just acts like a normal symmetry. And this is telling me there are still selection rules in place that protect the axion from getting a potential. Now we get to the real argument, which is good. So we have this non-invertible symmetry. It still picks some selection rules out for the axion, tells us it can't have a potential. But as soon as I add dynamical monopoles to my theory, now I can screen these Wilson lines. You can just think of it as creating a monopole here, and then out of that, these lines can stream. And so if I go back to my previous slide, right, you could probably get the sense that these loops can break open, and so this whole picture just kind of falls apart. And that's indeed the story. And so from that, we know that, well, indeed, as Clay and others have pointed out, the selection rule that otherwise protected the axion from getting a potential, that goes away with the possibility of these dynamical monopoles, exactly because they break open the loops. And so you can be led to speculate that monopoles must play some kind of role that's analogous to U1 instantons in this case. So this was kind of our first motivation. So thinking very hard about non-invertible symmetries involving axion-photon couplings told us that there's some kind of interesting connection between instantons and monopoles, again, worked out by Clay and others in a few years ago. Good. The second motivation, which is me as a phenomenologist, this was really my first motivation. In fact, this is what got me thinking about this, is Gigi Fan, Katie Fraser, Marius, and John Stout had this interesting paper in 2021 where they just had a free monopole world line theory. They just had a monopole, no interactions, it's just a free monopole. I study its world line theory. I force some periodic boundary condition. They found that studying that theory coupled to axions via this Witten effect that I told you earlier, that generates some effective potential for the axion. So this is just schematically what that potential looks like. They found that having loops of monopoles generates some potential with some coefficient CL times this exponential suppression, where MM is the mass of the monopole, M delta is the extra cost and energy to excite the monopole into a dion effectively. And cosine L theta is just summing over some integer L. So this is the potential they found. And interestingly, when they looked at the specific values for this MM and M delta, in particular for a UV completion where you get a Topf-Polyakov monopole, you might know that it's an SU2 where you break the SU2 down to U1 via Higgs. If they took that and looked at the BPS limit, so they took the Higgs self-coupling to 0, they found that this numerical free factor was exactly minus 8 pi squared over g squared. That's, of course, one of the most famous quantities in particle physics, right? This is just the BPST instanton action. And so they were led to speculate already in that paper back then that there is some kind of connection between these loops of monopoles and standard instantons, and that they might even be deformations of one another. Okay. So the takeaway is just that prior findings hint at a deep relation between monopoles and dyons and instantons, and that this relation is potentially of phenomenological relevance, right? It would be really interesting to understand this sort of mass generation mechanism. So, and I should also mention, this is of course not completely new. There have been previous hints in the literature that go much farther back in time. So these developments I showed you are really the modern ones, the ones that have happened in the last few years, but there's work by Clifford Taubes, Richard Bauer, Dyon, and others that kind of hint at this connection too. So it's kind of been hinted at for a very long time. That brings me to part 2 of the talk. So now we've motivated that there is some kind of connection between instantons and monopoles, and we want to study that connection very explicitly by constructing explicit field configurations of monopole loops and seeing how they relate to instantons. That's part 2 of the talk. So the starting point for, and this is where the new work really begins, is we're just going to take a Euclidean Maxwell theory in R4. So just give it some standard kinetic term. And we're going to add by hand some magnetic and electric current loops. So we're just going to by hand put down electric and magnetic sources in the theory that go in a loop in Euclidean space. And then we're going to study that field configuration and see how it relates to instantons. That's the plan. Okay, so to get started, we just begin with the standard Dirac monopole. So you might be familiar with the fact that if you just have a U1 gauge theory, and this is dating all the way back to Dirac, so this is a very old story, you're free to just write down a vector potential like so, where theta and phi here are just your polar, or sorry, your spherical coordinate theta and phi, right? So I'm literally just in spherical coordinates, just writing down some potential that I'm perfectly free to do. What you find is that this potential, if you just write it down, it gives you some magnetic monopole source, where M here will be the magnetic charge of the monopole, and then you have this sort of singularity right at the origin of space, out of which B field lines stream. That's these blue lines. So B field is stream. So that's the Dirac monopole. The Dirac monopole has this interesting feature in that if you use vector fields to describe gauge theory, it has a Dirac string. It's this unphysical singularity in the gauge field that you can move around with gauge transformations, for example. But this Dirac string, which is again an unphysical singularity, will feature in today's talk. So we just took the Dirac monopole and we made it go in a loop, right? So what I'm imagining here is I'm taking the Dirac monopole and I'm going to force it to go in a loop in Euclidean space. What you get is exactly this. So I'm imagining here I have some monopole loop world line. And to effectively regulate the theory, we like to think about having some little epsilon cutout around this loop defect. That's what this blue surface is showing. It's a little cutout around the monopole world line. And as you can probably guess, right, a Dirac string, which is just a string object, if you evolve that forward in time, that becomes a Dirac sheet. So that's just saying add a time dimension to a monopole, the string now chases out a sheet. That's what you're seeing here in the middle. So indeed, this is just some x-sized surface around the singularity, and this is my Dirac sheet. And throughout this talk, you'll see me occasionally use the coordinates r and tau, or you should just think of as sort of being locally pointing away from the monopole, and tau you should think about as parameterizing the length along this world line here. Good. So that's what we did. Now, you might realize that this is a squished down picture. Really, I'm thinking about a monopole in 4 dimensions, which will have some 2 surface around it, and then evolving in time in a circle, which will be, an S1. So really, the geometry here that the surface is around is a S2 cross S1. Because I can only draw 3-dimensional pictures at most, it has sort of been squished down into a torus. But it is really an S2 cross S1. That's an important point.
Your monopole here has infinite mass?
It has infinite mass. It's just some magnetic Dirac monopole source term.
So why put it in a loop, or there's no equation that this trajectory will be.
There's no equation.
You just put it by hand, yeah?
We just put it by hand. We're just studying the topology by now, which won't depend on the details of the equation, but you'll see what happens when we make it dynamical. That'll be later in the talk. Good. So, okay, so we did that. The next thing you want to do is you want to just add some electric current, right? So I can imagine I had some electric current that points in the tau direction, right? So it'll be with the loop following it around with the magnetic charge loop like this, right? So this is the S1 that the magnetic charge follows. Now I add some electric charge on top of that. Importantly, so this is a very subtle caveat. You actually need to pick this rho E to be smooth. This can be thought of as a way to sort of regularize the associated Wilson line here. I should say that the smooth charge profile can't be anything. In fact, we just took a UV complete monopole, projected out the Abelian degrees of freedom, and then used that to inform us about what the right choice is here.
Smooth means there's some charge off the loop.
It's not a delta function. It's not quite a delta function. Instead, what it's doing is it's enforcing this boundary condition right here. A tau on the loop is some constant. So that's kind of enforcing some holonomy condition right on the loop as I take this epsilon, this x-sized radius to 0.
Why is n integer?
Good. It's integer because then right on this loop, right, this you can show just becomes pure gauge. I can just write it as pure gauge. So it's like G inverse dg. And you want the U1 circle to wrap itself once as you go around the loop, kind of like a Wilson loop will. So you can think of this equivalent as some kind of Wilson Topf loop. But that's why it's integer. Generally, that we've thought a little bit about whether it might be okay to go, for example, half integer rounds, and it looks like in some UV completions that might make sense. But I won't say too much on that point because we're not quite done exploring that side of it. Okay. So it's integer because I'm thinking about going around my U1 group manifold as I go around the circle. That's why it's here. And so indeed, right, this is kind of like just the holonomy of a Wilson line. I integrate this and I get 2 pi times. Okay, so together, right, we have a Dyon that's a point monopole and then this slightly smooth electric charge profile. And again, just to emphasize this, and I just want to be super clear, this is very sensible from a UV completion point of view. Again, we just took a free monopole, say in a SU2 gauge theory, takes down to U1, and we looked at what do the abelian components look like. They look exactly like this. So this is literally what you get from a UV complete set. Good.
What's the scale in the UV complete setup of the width of that distribution on the right?
In general, it'll be related somehow to the core size. So I can imagine I take a very careful limit where
Well,
I
I guess I'm asking what factors of the coupling are there. Like, of course, yeah. So there's a
it'll be
map
like a
scale.
Higgs web, inverse Higgs.
Inverse Higgs.
Yeah. It'll be this M delta that I showed you originally.
Is this a Dyon with a quantized electric charge?
It will be if you integrate it over all of space. Yes, it'll be quantized. Yeah.
But in a UV description of dyons,
Yes.
as classical solutions,
Yes.
there's a collective coordinate.
There's a U1 collective coordinate.
And if you're going to treat that as a configuration in Euclidean space, you would integrate over a collective coordinate rather than quantize it.
Integrate in which sense? Sorry.
In the sense that when you do instanton calculations, if there are collective coordinates for the
Yes.
instanton,
Good.
then
Good.
you integrate over the bosonic collective
Good, good,
coordinates.
yeah,
You
yeah.
don't quantize them first and then
Good. Good. Good.
integrate.
Yeah.
You
Good.
integrate over the collective coordinates.
For sure. Yeah.
So-
So what you're talking about is in fact more reminiscent of Matt Reese's thing, where you treat this collective coordinate as an extra dimension, like an extra, I can think of it, coordinate dimension that I add on top of my 4 dimensions of space. And then when I compute these instanton effects, I'm integrating over this entire like 2 pi period of the collective coordinate. And that's certainly a way to get these instanton effects. We're just doing the simplest and dumbest thing you can possibly imagine, which we're just saying, put down some electric and magnetic current loops and see what happens and see whether there's some notion of a quantized instanton number. And you'll see that there is.
I'm willing to believe that you'll get a quantized instanton number. I guess I'll wait till you talk about the UV completion,
Yes.
because it
Yes.
seems to me like a weird thing to do from that point of view.
Sure, yeah, you can certainly, yeah, there's certainly another approach, which I think, so I'm thinking about at the moment, a sort of more operator-based way of constructing this story, where I'm not thinking about bulk field configurations in the same way. I'm instead thinking about operator insertions. And I think that view is more probably, but remember that ultimately, right, this U1 collective coordinate, it comes from integrating out these bulk gauge fields. Say you have an SU2 UV completion. That, of course, if you have a Dyon, just a static Dyon, for example, that has some field profiles. There's no notion of sort of a world line collective coordinate the way there is in a world line description. The way the world line collective coordinate emerges is you integrate out the bulk fields, which is why there should always be sort of a bulk field view of viewing these quantities, including the electric and magnetic charge. But I'm happy to chat more after if you have more subtle thoughts. Yeah. Okay. So good. So now we have made the setup, and now we can just compute the U1 instanton number. So here I've just written FF dual as F wedge F as kind of a way to emphasize its topological nature. This thing is actually perfectly integrable over R4, even as I took that excision size to 0, in spite of this Dirac monopolar singularity that you have. And there are many ways to evaluate this quantity. So I'm going to show you 2 that I think are both enlightening and showing different aspects of this configuration. So the first thing you can do is just, if you're ever somebody who has thought about axion direct detection, you know that F wedge F can always be written as E dot B. And when you write F wedge F as E dot B, it just becomes blatantly obvious, right? Why a Dyon loop should have instanton number. What is a Dyon? A Dyon is like the quintessential object that has parallel EMB lines coming out of it. So of course, when you integrate out some loop of Dyon, that's going to give you something non-zero here. So of course it has some topological instanton number. And so indeed, you just proceed with the computation, and you'll probably believe me if I tell you that this is a way of writing the electric field, and this is a way of writing the magnetic field integral. What you find is that you get minus m times n, where these were the 2 integers I showed you before. One was the magnetic charge of the monopole, and the other was this electric charge or holonomy, depending on how you think about it.
But that holonomy, was that holonomy quantized just from the infrared point of view? If I'm just a U1 effective field theorist, would I have been forced to take
No.
n to be integer there?
No. You can have it be fractional. And in fact, it looks like in some UV
Exponential,
completion,
or why not even continuous?
or maybe even continuous. It is possible. We wanted to make
I
sure
know you
just
want to match, so you're trying to do something reasonable from that point of view, but
Yeah.
I'm just trying to
Yeah.
understand from the purely infrared point of view. Could you have had that n be anything?
in principle, yes. Yeah, I think so. But again, this is kind of in thinking about good Wilson and 't Hooft-line quantization conditions. That's exactly what's forcing you to confront questions like this. But indeed, we studied an explicit example where this thing was 1/2 and this thing was 2 effectively, and that seems to all be kosher. But there might be some subtle questions here about the quantization condition. What we're doing is we're just imagining, okay, like this is some integer
Yeah.
quantized Dyon, and so we just have everything be integers. But indeed, like there might be good generalizations for this. Okay, and so again, the reason I really like this particular derivation is it just like makes it so obvious why Dyon loops should carry instanton number. It's again just the thing that has parallel EMB.
And just another clarification
Yes.
question, this is completely insensitive to the trajectory.
This is completely, as long as you always scale, say, the holonomy with the length of the trajectory, then
Such that the total integral is say n,
exactly, yeah.
but there could be a arbitrary
Could be
thing.
some crazy shape, yeah, we're just, because we wanna ultimately UV complete this, right? The simplest UV completion where we have some nice symmetries that help make that numerical evaluation eventually simpler, is just to have it be a circle. That's the easiest object to study, but in principle, yes, you could have this be any sort of arbitrary trajectory. So the other thing you can do is you can, that I think another way to evaluate the instanton number, which highlights its sort of topological nature, is you can just use Stokes' theorem and you can convert the integral over f wedge f to an integral of this thing called in this case, the U1 Chern-Simons current over all singular surfaces in your theory. And there are in particular two surfaces that contribute non-trivially. You will both have the surface around the Dyon world line, and you'll have a surface surrounding this Dirac sheet that I showed you earlier. So to show you, right, you'll do one integral over this, what looks like a blue 2-dimensional surface, but which I told you is really a squished 3-dimensional surface. That's secretly what this is. And then you do an integral over the surface that wraps around this Dirac sheet. And really they form sort of one continuous surface.
Why do you keep emphasizing the direct sheet? It's not observable or visible in any sense.
It carries information about the instanton number. So when I evaluate this integral, I can't just evaluate, well, I can always convert my integral, if I just do an a of f wedge f equals integral, a wedge f, I need to integrate that a wedge f both out here, but also in the middle.
Sure, you have patches. Is
They
that
have
what you're-
patches, yeah. But I can always move the Dirac sheet with a gauge transformation. That'll just change where the singular point is. But there is a description, of course, where I just use patches and not a single gauge field. But in the single gauge field prescription, your Stokes theorem tells you should integrate everywhere where your field blows up, where you have some singularities, and that includes the direction. Of course, we've just to build your confidence, we've of course verified this in many different ways, right? So you can integrate E dot V directly, you find the right quantized thing, and you can do the surface integrals. That also gives you the right quantized thing. And indeed, you find that you kind of get a factor of 1/2 from this integral and a factor of 1/2 from this loop. So skipping over steps, so skipping over the factor of 1/2 that comes from the Dirac sheet, what you ultimately find is that this f wedge f integral just simplifies to, and this I believe is somewhat invariant under this prescription of the Dirac sheet, for example. An integral again of just around this holonomy along the Wilson line or along the world line of Dyon times an integral over an S2, where this S2 is just the surface that surrounds my monopole at any point or Dyon at any point along this circle, right? So if I just look at this fixed point here, what I'll see is I'll just see a monopole sitting there with some true surface out of which magnetic field lines stream. And that's what this second integral counts. It's just counting the magnetic flux coming out of the Dyon, right? This is kind of the definition of a magnetic monopole, that this thing has to be quantized. And this is the integral along the world line that we saw gave 2πn. And so again, right, you can see that this ends up just giving me minus n times m, right? If I just plug these two quantities in. And I like this approach because it exactly shows how this integral is topological in the sense that it becomes kind of an integral around these surfaces around both the direct singularity, the direct monopole singularity, and around the direction.
So if you're thinking of these as instantons, Euclidean field configurations, are you also integrating over some kind of space of embeddings of these loops in R4, the orientation, the size?
That's what we're just about to hit now. Is we're going to start thinking about the currents as dynamical, because of course, like I can put down any currents I want by hand, but those should ideally also solve some equations in motion. And this is where you'll find that there is some deformation you can make in a proper UV theory, where you show that this loops of Dyon actually becomes a standard instanton. So that's where we're headed indeed, is to think about these questions. But first, while we're sort of fixing the currents by hand, and we're just studying the U1 instanton number, this is what we get, right? So I'm going to integrate the EMP field, so I integrate the Chern-Simons current. What I always get is minus n times m, which itself is integer quantized. Now, in a completely UV agnostic theory, maybe you can think about whether n could possibly take on some other value, but at least in our simple UV mesh story, this thing becomes integer quantized. So again, just to hammer that point home, right? M is the magnetic integer, and n is the holonomy, which I think about proportional to the electric. So before we get to the action and think about varying these current loops, we should first just ask the simple question of how is this even allowed, right? So standard lore says there are no Abelian instantons, and the reason that that is true is just typically stated this way: the third homotopy group of U1 is trivial. What the statement is telling you is a U1 gauge field doesn't have enough structure to wrap non-trivially at an infinite space-time distances. That's exactly what a normal instanton does, like an SUN instanton has some non-trivial structure out at infinity, at least in some appropriate gauge. But U1 gauge fields don't have enough structure to do this. So how are we finding, integer quantized instanton numbers in our U1 theory? It's not really that we're violating this common law that people understand, but it's just that instead of thinking about R4, when you put in a direct monopole, you're effectively punching a hole in the space-time. You're punching a circle in the space-time. And so now the manifold you're really looking at is an R4 subtract S1. And so then, right, you can have these topological bindings given by these two, in this case, integers again, the magnetic charge integer and the electric charge integer. So that's how this Abelian instanton, which we've sort of put down by hand by putting in the current, is allowed. So before we move on to the action, which is, oh no, I spoiled my surprise. Before we move on to the action, which is the next part of the talk, I just wanted to highlight what this kind of looks like, right? So we have a U1 manifold, which I can think about as given by some series of colors. So I can imagine as I traverse my U1 group manifold, I go from white to red to blue and then back to white. And the way that this Dyon loop works is just visualized here. The holonomy, which corresponds to going the long way around the loop, right? So this is literally, again, just showing the Dyon loop in a different way. As I go around the line, the holonomy winds from 0 to 2 pi, right? So it goes white, blue, red, and then back to white. That's where one of these integers is coming from. It's a mapping from the holonomy onto the U1 gauge group. The other integer is coming from, I'm wrapping the other way around. So I'm going around the inside of the bagel. This corresponds to going around the equator of the monopole. So you might know that there's this sort of two-patch prescription for describing a monopole where you just look at the gauge field right at the equator of it. That tells you how its magnetic charge is quantized. That's what you find from going this other way around, right? So if I go the other way around the donut, I go from white to blue to red and black to white. So I go all the way around my circle. So that's kind of the class of maps look like this, which I thought was kind of funny. And of course, I spoiled it. But I'm coming to you from New York, where we have our famous rainbow bagels, which hilariously have exactly the same topology, right? I go this way around, I go around the rainbow.
Rainbow bagel has a flavor.
No, it's just pure food coloring. They're actually kind of awful, I'm not gonna lie. But to celebrate this paper coming out, we did go out and grab some, even though some people consider them atrocious.
The schmear, I hope.
Okay, now let's get to these questions, these great questions about the sort of dynamical nature of the monopole. So naively, right, if I have some Dyon loop, and this was worked out by other people way before us who thought about monopole or Dyon production in background electric and magnetic fields, they naively have an action that looks like this. So it's 2 pi times the radius of the loop times the mass of the Dyon, and then some other term that scales with the charges and the gauge coupling. So if you look at this very naively, right, it really looks like, to minimize this action in a fully dynamical theory where I also allow my currents to change locations, which I should in a fully sensible UV complete theory of these charges, it really looks like I want to take R to 0, right? So it really looks like the loop just wants to shrink and shrink and shrink and shrink. But of course, we run into a subtlety here.
It looked to me like if you want to minimize S, you take M and N to infinity.
Well, okay, so suppose I have fixed charges. Suppose I have fixed charges. So I have some electric and magnetic states. Suppose I have fixed charges, then obviously R is going to shrink. But yeah, I mean, if I allow the charges to change too, then yes. Good. So naively, this prefers to shrink to 0. But of course, we know that as I shrink my loop more and more and more, these dyons, which are really not fully kosher U1 objects, right? They really have some core size that we expect comes from some non-Abelian theory, or could even be from some more exotic monopole, like maybe a KK monopole. There will be corrections to this action. So L here is a schematic for the size of the Dyon. We'll have corrections like this that actually blow up as you take R to 0. So it looks like in the pure U1 theory, this loop we kind of just put in by hand. If we want to extremize the action associated with it, we want to shrink it down to 0. But I know I can't do that in just the pure U1 theory because I need some kind of input from the UV. So that really tells you that to really understand sort of the nature of these, what you might call Abelian instantons, you really need a full UV theory. And so the takeaway is indeed, so we've shown that a Dyon loop, if you just plunk down the currents by hand, it carries an instanton number. But in the pure Abelian theory, it clearly prefers to shrink to 0, at which point the loop is so small that now the radius of the loop is comparable to the size of the Dyon core. And so clearly, once it starts to self-overlap like that, you need input from the UV. So that brings me to part 3 of the talk, which is talking about the UV completion. So to understand what the heck is going on here and what actually is happening with the action, we just looked at the simplest field theoretic UV completion of these monopoles that we could find, which is of course just the Georgia-Glashow model. So the Georgia-Glashow model has a Euclidean action that looks like the following. You have some SU2 gauge field, and you have some adjoint Higgs that via its potential here breaks the SU2 down to U1, right? So this is known to give you the so-called Toft-Polyakov monopole, which is definitely the most famous UV complete monopole where it has finite energy and finite action and so on. Lambda here is the Higgs self-coupling, which sometimes you see people take the BPST limit. That means they take lambda to 0. So the plan now is just to basically do the same thing we already did in the U1 story, which is we just want to construct this Dyon loop topology in the UV theory. We want to, because these equations are very nonlinear and difficult to solve, we want to study what happens when I just numerically solve the field equations. And to help us do that, we're at first going to look at fixed R. So for fixed radius, what does this configuration look like when I just minimize the action? And then finally, we're going to see if we can sensibly relate this story back to the U1 Dyon loop that I construct. So like I said, and that you might know or maybe not, depending on how close you are to these fields I'm talking about. This model, like I said, it admits a Toft-Polyakov monopole. So that's just characterized by this famous sort of hedgehog configuration, at least in one gauge, which is I make the Higgs field for a static monopole just point radially outwards from the core of that monopole, right? The Higgs is a adjoint, so it has 3 indices up here. Phi naught is just the bev of the Higgs, and h of r is some interpolating profile that goes smoothly from some number at 0 to some number at infinity. That's not quite gauge invariant, but it's just some smooth profile. It doesn't really matter too much to our topological story today. to get the Polyakov monopole, you want to match this Higgs field to a gauge field configuration that looks like this, where again K is just some smooth profile. And the result of doing all this is you just get in this hedgehog in the Higgs, and then you get some B field source. So that's the Polyakov monopole. What's perhaps less known than the Polyakov monopole itself is you can promote it to a so-called Julius E Dyon, and there are many different ways of thinking about this. One of the simplest from sort of I want to study bulk field theory point of view is just you can add an extra A0 component on top of the components that I just showed you that is isospin aligned with the Higgs and has some other interpolating profile. There are different ways of thinking about this. For example, if you have this U1 collective coordinate story, that becomes especially clear if you do a gauge transformation and take this from a constant time pointing component into a time dependent spatial component. You'll find that time dependence is kind of what gives you this U1 collective coordinate. And of course, for my Dyon to be properly quantized, I have to pick some asymptotic profile for GOR. That's specified. It's not important. Okay. So we want to embed this construction in R4, and because we want to do numerical relaxation, we better not have any singularities. And unlike the Dirac monopole, which is inherently singular, it's possible to not have a singular Dyon loop field configuration if we resolve the core in its UV physics.
Before you discuss the numerics though, could you say like analytically in principle, what is it that you're trying to do? You eventually resort to numerics, but what are you trying to do?
Good, and that's what I'm going to talk about now. You might appreciate this. So I hope this answers your question. If not, please ask it again. But so I want this hedgehog topology, right? I want something that locally looks like a monopole, both in the Higgs field and in the gauge field, both really close to the defect, and also out at infinity. And so it turns out that as you begin to think about how do I embed a hedgehog into a loop, right? You don't want any singularities. You don't want like a hedgehog here and a hedgehog here. They point towards each other. There's clearly some kind of singularity going on there in the middle. To do this embedding very carefully, and this is related to some older papers, you actually end up being forced to adapt this type of hope map, which is kind of interesting. So that's saying, and this is somewhat a curiosity, so it's not super important to today's talk if you're not too familiar with this type of story. Let's check the time actually. We're good. The hope map is just saying, okay, my Higgs somehow has to be configured at infinity so that it maps spatial infinity onto some S2. S2 here is the Higgs group manifold, right? So it defines SU2 mod U1. And what that looks like is, I can imagine I take my Higgs isospin configuration at infinity. That's a 3-sphere. I can stereographically project that down to an R3, and then I can squish that R3 down into a ball. What these types of maps look like is exactly this. There are some mapping in color here from a 3-dimensional space onto a 2-sphere. So you can think of all the purple points here along, because it's a line really, mapping onto the purple part right here, for example. So
Could I just follow up on Clay's question?
Yes.
Briefly, is the goal to show that in this smoothed out version, you can construct something that has instanton number, or is it as well to show that it solves the equations of motion?
It's to construct something that has the right U1 instanton number. If you look at the U1 degrees of freedom, looks like a Dyon.
Be a solution to the equation.
For now, it's not solving, but I will show you what the solution is. So we will ultimately see what the solution is that comes out of all this. And lo and behold, you're probably not surprised to learn it is a standard instanton. So this thing really wants to shrink to 0. And what you find is actually this, what looks like a Dyon loop, really when you extremize the action, just becomes a Higgs BPST instanton.
But there is no critical minimum for the.
There is no critical minimum. So we're on a lattice, so we have some
So
size.
it shrinks to 0.
But it shrinks to 0, yeah. So if you just look at the equations of motion, unless you use some quantum corrections to stabilize it at some finite size, it just wants to shrink and shrink and shrink all the way to the edge of configuration space. Yeah.
So why not just use Affleck's constrained instanton formalism where you fix the size of the instanton?
So we've thought about that a little bit, right? But we're on a lattice, so we actually have the perk of.
But, I mean, all right, you don't have to be on the lattice. You just want to do a calculation
You
to
just want to do it.
understand something about axion physics. So why not use that formalism that was already developed?
Because so Affleck just fixes some instanton at some fixed size, but we very particularly care about how the loop deforms into an instanton. From Affleck's construction alone, it's not obvious that looks like a Dyon loop at all. That just looks like some instanton I fixed at some finite row, some finite size. We really care about this loop, and we want to understand how the loop interfaces with the standard instanton. And so, right, this is all related to Affleck's formalism and to calculate things, which is a wholly separate question. I'm just telling you about topology here. That is indeed a reasonable approach, right? That's really what you want to do. But for just studying these loops, right, we're trying to bring clarity to Matt Rees's paper, for example, and some of these non-invertible stories. You really want to see what happens to the loop itself and not just some instanton you've immediately fixed to have some finite size. Does that answer your question?
Yeah.
Okay. And if not, I'm always happy to talk more later.
But Matt Rees's calculation, if I remember correctly, there is almost like there's a fixed radius.
There's a
Saddle point.
There's a saddle point, but that saddle point is actually good. So that saddle point is actually a fixed x mu. So it's a fixed spatial location, and the Swinger proper time is actually in this internal U1 collective
Right.
coordinate. So that thing is actually also 0 size, and so somehow they've maintained the correct topological information, and including this U1 collective coordinate. But so his thing is spatially actually also a point. That's what they're expanding about. In fact, we had this discussion with him after this paper came out, and it was quite enlightening. Yeah. So if you read the paper, it says fixed x mu, but some finite Schwinger proper time. That's all in this extra fifth dimension, which is the U1 collective. Okay. So just suppose that I'm doing, I do that. I construct this hook map. If I just look locally at slice through the Dyon loop, it'll look like the following. So here I have my loop, and I imagine I just cut it right across, right? So in that case, these two opposite points of the circle will become like a monopole, anti-monopole in Higgs isospin space, right? So this is showing the direction of this Higgs 3 vector. You see that clearly, right? It looks like a hedgehog up here, and it looks like an anti-hedgehog down here, which is exactly what. Now, we want to match the gauge field to the Higgs. That's necessary to get finite action. So you need to have some term like this in your SU2 gauge field to not have infinite action as you go out to spatial or space-time infinity in this case. And then on top of this piece, which is matched to the Higgs, where k is some profile function, you also have some extra Abelian degrees of freedom in the gauge field. That's, of course, just saying that anything that's isospin aligned with the Higgs is sort of invisible to the Higgs, in that's in the unbroken U1 sphere. There's also an extra term here that I haven't written that's kind of smooth wiggles on top of this, but that's not important to the topology, so I just haven't written it down. Okay, so if you want to gauge match so that this close by looks like a Dyon loop, so you have this hedgehog close at some fixed radius that you've picked for now, fixed radius. And you look at it at infinity, if in both of those domains you want this thing to really look like a Dyon loop, you in fact already find that you're sort of forcing yourself into this minus n times m instanton per sector. And so now we want to relax the field configuration. So now I forced this topology to look like a hedgehog, and I have some asymptotic boundary conditions that tell me that this should look like a Dyon loop. We just take that, and at every fixed radius for this loop, and eventually we'll see what happens when we take that radius to 0, we just do a numerical relaxation on a lattice. And that, of course, gives me the semi-classical solutions to the field equations with some constraint for now that there's some finite radius hedgehog configuration. And so if you just look at that, indeed, you find something, again, we're fixing the radius for now, that really looks like a Dyon anti-Dyon. So if you look at the B field here, this is the same cutout that I showed you before. Here you have a anti-monopole, and here you have a monopole, some very localized purges. And if you look at the electric field too, it also really looks like a Dyon loop, although you might already see that in fact,
They're not widely separated, right? Like
they're not widely separated. For now, they're really
scale is that one unit there is what, the Bev?
Bev, that's the Bev. Yeah, and then of course gauge coupling is 1, and the Higgs quartic is 1. So just to keep everything else is 1, and this is units of the Bev. You might already think this looks a little bit weird, right? Like here, clearly I have the fields be very large right on the defects, but here they're sort of larger in the middle. And that's already beginning to show this fundamental tension there is, which is if I go to even larger separations, and now there's 2 times the Bev, inverse Bev, distance between these monopoles or dyons, I still get something that really looks like a really nice Dyon or monopole, anti-monopole up here with sort of these very nicely localized charges. But here, things begin to look weird, right? Like the field strength is very big right in the middle. That's not what we associate with normal point charges. And you can even see that the maxima are kind of slightly displaced. And what is this really telling you? This is really telling you that in this topological sector you fix, there's a tension between this Dyon loop that you're trying to impose by hand, and then the instanton solution, which turns out to be the real solution that really solves the equations of motion, everything left free, no fixed radius, no nothing. And so clearly what is happening here is even though you're trying your hardest to force topology to make this thing look like a Dyon, the fields want to continuously deform down into just a point, an infinitely shrunk instanton in this case. Although we can't shrink it infinitely because we're on a lattice, and so the lattice spacing actually sets kind of a cutoff for us. And so indeed, right, if you just look at the action as a function of the loop, of the radius of this loop, what you find is the following. So there's sort of a bunch of terms here. I just want you to look at, for example, the blue dashed curve. What you find is that at really small radius, you go exactly to, this is exactly 8 pi squared. And remember, I had said g equal to 1. So this is literally 8 pi squared over g squared. So if I allow this radius to shrink and shrink and shrink in the UV theory, what I end up getting out is the BPST instanton. And of course, again, it's stabilized at some finite size due to our lattice spacing, but really it wants to shrink infinitely down to be infinitely localized if you let it go in a continuum. And as you go the other way, right, clearly there's no signs of any saddles or extrema of the action in any sense. The action just grows and grows and grows. So clearly there's no actual solution associated with the finite size loop. Like clearly the only solution you get is when it shrinks to 0 and becomes a standard instanton. And you can in fact prove this pretty easily with a version of what's called Derrick's theorem. I don't know if any of you are familiar with that. Yeah. So that's the first takeaway, and I should hurry and wrap up. It's a Dyon loops are just a deformation of standard BPST instantons, at least in this UV completion that we've studied, and they have higher action. So why do we care about them at all, right? Do they have anything interesting to say at all? Well, this is where things get really cool, and I want to hurry and show you what happens in the last 2 minutes, which is, let's now just look at this loop. Let's just accept that it's sitting at some finite radius that we fixed, and let's project out the Abelian degrees of freedom. So I comb the hedgehog. That means I do a singular gauge transformation that takes the Higgs field and forces it to point in the same direction everywhere in my space. Then I can very easily just define my Abelian gauge field as the third component of this SU2 gauge field. And then I'll have my non-Abelian stuff all packaged into this W here. What that looks like in pictures is the following. Again, like I've just done a singular gauge transformation that combs the Higgs, it makes the Higgs point in the same direction everywhere. And the price I pay is in the Abelian subcomponent, the third component of the SU2 gauge field, I get the reemergence of a Dirac spring. And so the Abelian Dyon loop returns. So if you just look at the Abelian component, it really looks like the thing I showed you in part 2 of the talk, with the singular defect and the Dirac sheet. And here's the really cool thing that's kind of the punchline of the story, which is if I even go and look in this stage where I've separated things out very nicely at the non-Abelian instanton numbers, and I've traced G which G, the non-Abelian gauge field strength, and I look at how that breaks into an Abelian and a non-Abelian subcomponent, I actually find that only the Abelian subcomponent, even in the fully UV complete theory, carries the instanton number. And it's again just minus n tandem. And so the W contribution, the non-Abelian contribution vanishes trivially, and the instanton number is really only carried in the Abelian subsector, which I think is just so cool, right? Because this lends some credence to the fact that there is maybe some sense in thinking about this object as an Abelian instanton, even though really we know it's kind of a deformation of a non-Abelian instanton in the UV. There's still some Abelian topological information that's carried by that pure Abelian loop that can tell me that there's some kind of instanton here that might have some physical effects. So that's takeaway 2. Projecting it.
Can you just explain once again the separation? How are you splitting it? So you're imagining some SUN or something in the UV?
Yeah. So I'm again just in this Georgia-Glashow model.
What's the split into Abelian, non-Abelian?
So this is the thing that's, so I make the Higgs field point in the third direction everywhere, right? So it's just pointing in delta V3 everywhere. And the gauge field component that's aligned with the Higgs, right? That's the unbroken component by definition, in fact.
This breaks down at the origin where phi goes to 0. This is the model.
Yeah, it's a singular gauge transformation.
It's a singular gauge transformation.
This is the thing that's sometimes called singular gauge.
Yes. So it's related to singular gauge for instantons too. This is a singular gauge transformation. So this is perfectly allowed, like the action of the configuration is still perfectly finite. Even though there are singularities, they all show up in this field. But if you actually compute the whole action, you'll always find that the W comes and rescues you. Whenever you think you have some kind of singularity that gives you infinite energy or infinite action, you'll find that the W components always end up canceling those in a convenient way. Is that clear?
You're saying that the instanton number is completely carried by the Abelian component?
Yeah, so you just do this separation for this Dyon loop construction we had. And a little bit, I mean, at least at the time, I thought it was a little bit miraculous that if you then just break this into contributions from A and contributions from the W component, this thing just vanishes. In fact, it vanishes trivially. In that you're integrating this, in this case, along singular surfaces, and you find that the integrand here actually vanishes right on the loop or right on this sheet where you might want to try to integrate this quantity. Of course, this is not quite a gauge invariant statement, right? But you can analogously construct some gauge invariant definition of F and integrate F wedge F, so the Abelian field strength defined in a gauge invariant way. And of course, you would find that this is equivalent to this. So there is really some sense that it's gauge invariant in which the instanton number is carried by the Abelian subcomponent. That's the claim here. That's really one of the punchlines.
This has to depend sensitively on the topology of your spacetime.
Yeah, obviously, if I compactify or something, then
Even on a torus. Even on a torus,
yeah. On a torus, you can already have Abelian instantons without monopoles, right? If you compactify all four space-time directions, say into two circles, or sorry, two spheres. So yeah, obviously, this is all saying I'm in R4 and I'm putting down these defects. If I go to some other geometry, then or some other topology, then the story changes. Okay. So I have -3 minutes, but this is thankfully my last slide before the conclusion, right? So what about the axion, right? So I've shown you all this sort of rich topology that I certainly think is very exciting, but how does this actually connect back to the axion? And that's kind of an open question for now, right? So we showed, Marius has this paper where he shows that you can sort of approximate, and I think Clay has made use of this too, down to a squiggle, some of these instanton effects using just monopoles, using just, say, the mass of the monopole and then the mass of the dyons of your theory. And the question is, does this sort of Abelian instanton language allow you to say something about instanton effects without knowing the details of the UV physics? So I don't know. That's where I'll leave an open question. And I think, in fact, that Clay and Dyon are thinking about these types of questions a little bit. But the dream scenario would be, right, that I might not know where my dyons are coming from, which UV completion they're coming from, but just knowing they exist, I can already begin to compute, and knowing their masses, I can already begin to compute some instantonic effects. That would be kind of a superpower if that could work. So this might be phenomenologically interesting, and again, some people in this very room are thinking about this. So that brings me to my conclusions, and I'm so sorry about going a few minutes over time. So I just showed you that the axion shift symmetry breaking has points to a sharp connection between Dyon loops and instantons. Then I showed you that Dyon loops are effectively U1 instantons that beg for UV completion, right? They want to shrink down. Then I showed you, at least in this simple UV completion, SU2, of course you expect it's generalized to SUN. These Dyon loops are really just deformations of standard Higgs BPST instantons. And finally, as I hinted at, right, this begs for further exploration. Can I maybe compute physical effects using these Abelian instantons? So that's the talk. Thank you very much.
Thanks for questions and comments.
So a precise connection between, a couple of things I'm a little bit confused about.
Yeah.
But the instanton computations themselves in 4 dimensions are ill-defined, typically. And you can try and use constrained instantons or some other approach.
Yeah, in a Higgs theory, yes.
Higgs theory,
Yeah.
and none of it is very clean in 4 dimensions, and often we'll give for more complicated gauge groups will give wrong results. But but you can directly connect to monopoles and instantons by compactification to 3D and then
Good.
Abelianization, right?
Yeah,
That seems
I was
to be
just talking to these two, especially Clay earlier, and this is exactly what they're trying to do to make this mapping work. So I've shown you.
That's the old, that's a relatively well understood story from a while back.
Yeah.
And then you'd ask, are your observables computable in the compactified theory, and then how do they depend on the radius?
Yeah.
And then try and take a limit. And there's an extra monopole in there, there's KK monopole you have to worry about.
Yeah.
But it works. I mean, there you get correct versions of
Mhm.
4D instanton computation.
Yeah.
And there's kind of a clean.
Yeah.
Is your circle somehow gonna end up being this, your loop?
I don't know. So this is all embedded in R4, right? So we don't have, when you compactify a space-time, it's a lot cleaner because now you really just have a free Dyon sitting there evolving forward in time, and then it's automatically compact because the time direction is compact really. In our case, right, what we discovered is there's all sort of subtleties when you try to embed that in R4, but there are definitely links to this story where you've compactified one of the dimensions. And again, I think if you talk to Clay and Leontow, in fact, that's something they're very actively thinking about right now. So
Yeah, I mean, if you just leave it in R4, then first of all, you don't really have a solution to the equations of motion.
exactly, yes.
So they're going to be 1-point functions. Secondly, even if you just look at the quadratic fluctuations, they're probably negative modes. So you're going to get like imaginary parts of your action.
Yeah.
I mean, it sounds,
Yeah.
it sounds very, I don't know how Matt Rees and company dealt with this. Probably they just didn't deal with it.
Yeah, indeed. So a more clean mapping between, especially for computational purposes, the instanton and the Dyon loops is an open question again. This is showing that the topology at least works out to say that there's some connection that is clear, but for actually like computing things in my path integral, summing over, you know, some instanton expansion, that's a whole open question that this technology we developed can't on its own handle yet. But it is a very interesting question. I think that is worth answering. Again, some of your colleagues are thinking about it.
A question on the comments.
Yes, sir. So can I ask so can you comment again on the gauge invariance of the statement that that this comes from some the Abelian part of the SU2?
Yeah, so obviously the Chern-Simons current here is not gauge invariant,
Right.
but I can always imagine instead of writing this as A wedge F, I can just write Abelian F wedge F, and then instead of integrating over my surfaces, I integrate over all of space-time. There's a non-gauge invariant way of defining this capital F here, right? It's just a field strength. And so if you do that, then it's a gauge independent statement. But the cleanest way that connects with the topology is always to do these kind of Chern-Simons current integrals, which is why I like this parameterization so much. So is that clear? If I integrate cap curly F, which curly F, that thing is gauge invariant, assuming you've picked that definition for that field strength. The gauge invariant definition, yeah.
Like trace of phi with times F
Yeah, exactly.
times G, I guess.
Yeah. So yeah, I probably gave you the impression that there's many open questions here, and that's definitely true. So I always welcome any conversation.
Yeah, this thanks Marius again.
It makes sense for me, like, I don't know, like, when I read some of them,